curso de hoje, Mariel, todo com você.
Okay, so my lecture today is a little bit ambitious because I want to talk about singularities in main character flow. That is, it has been a very active research field for the last 30 years. So of course I won't be able to say everything, but I'll try to summarize a lot of things. So let me try to make a little summary of the things that I'm going to say. So if you're lost, at least you know where I am maybe, or where did you get lost. I'm going to start with an example. Or maybe more than one. Then I want to talk about the case of curves that is sort of special. This is for today. And then I want to classify singularities. In two types, type 1 and type 2. Not very creative names, I guess. It works. And last, I want to talk about how to continue the flow. Let's continue. After singularities. So as you see, it's a little bit ambitious. In the notes, there are some proofs. I don't know how much I will be able to prove today. So I think I'll just give you a lot of results here, and maybe at the end we can decide how much can we prove of the things. So let me start with the example. Well, the one that we already talked about is spheres. And this we know that converge to a point in finite time. And we saw that the evolution of this is given by a sphere of radius RT that is exactly 1 over square root of 2 or R0 to n 2n t. So that implies in particular that the second fundamental form is something of the form there's some constant here, but something of this form, sort of. There's, like a constant there that you can, where t is the singular time. Well, with cylinders, we have the same phenomena, and the example that I want to talk about is when you start with an initial condition that is what they call a dumbbell initial condition. So this is supposed to be smooth here. Here you have some epsilon. Here you have some r. So just intuitively, if this is really like a cylinder, of course this is not going to be a cylinder for all the evolution, but if the shape is more or less preserved, this is moving this way. So this is trying to flow that way. So that's the direction of that. And this is flowing that way. And then it's not clear that if this is going to exist as much time as this one. I mean, this seems to be, if this is big enough, this seems to be have a longer existence time than this here. Of course, this is not a sphere. But what one expects for something like this is that you will have a singularity that is like this. So it's a different type of singularity. And let me give you like an idea of how you could prove this. How to prove this. Or how to construct an example like this. And one idea here, there are other constructions, but the one that I'm going to show you here is consider the following hyperboloid. Consider this. I'm going to write it like this. R and cross R. Such that I should check that the signs are correct here because it's important for this to work. I'm gonna call this M of t, or maybe N of t. Let me check the constant there. Well, so this is something that looks like this. So this is something that looks like it's a rotationally symmetric surface. I'm not very good at drawing. And here you have that this is opening up. Rotationally symmetric. But this is well defined as long as this is positive, because I mean, this is well defined here as long as this is positive. So this is just for t less than epsilon squared over 2 beta. So an exercise is to show the following. I'm not going to do it, but you can do it, I think, easily. If you take this as f, df dt dot the normal minus h, it's or plus h, I guess, is something that is positive for some beta, for beta n well chosen. And then if you use the maximum principle that we saw yesterday, you can see the following. If you have that M0 is contained or in the set of the x hat xn plus 1 such that, so what I want to say, if it's included here, is if it's included inside, so n minus 1 minus beta xn plus 1 squared less or equal than x hat squared minus epsilon squared, then mt is going to be included in the evolution of that. Plus 1 squared x hat squared And that means the following. So in this picture that I have here, now I can try to draw a big ball here of radius r. Big in the sense that it's big with respect to this epsilon here. And another big ball of radius r. And then when I have an initial condition, there is a dumbbell shape that goes outside all this. So this is going to be my M0. Then this part can exist at most for this time. But if the R is big enough, this part can have disappeared before that time. So in fact, I'm going to have something that may look like this. It's not clear from this example, though, that if I have here one point or maybe one line, and it looks like this, that part is not clear, or how fast the singularity is forming. But it's clear at least that I will have a singularity that is not like the sphere, and that sort of separates this in two parts, into regions. Okay, so having that in mind, let me say a little bit about the curve case, and I'll give an example that I won't compute anything. So let me think about a curve that looks like this. So what is the evolution of this curve? This is an old example, and it's sort of unclear what happens, right? Because the curvature here is very big, but this could be very thin. So it's not clear if this is going to go faster this way or it's going to collapse, like my example there. And actually, what happens with this, you can go to YouTube and search for curve shortening flow and see what happens with this curve. So what this curve is going to do is that it's going to unwind faster than it's going to collapse this way. So in some time, it's going to be still windy, but less. And then eventually it's going to become actually convex, and it's going to converge to a point. It's not very clear at all just by looking at this picture, but there are these theorems from the mid-'80s that state the following. So in this case, mean curvature flow was known as curve shortening flow at the time. It's still known as curve shortening flow. This is greater than equal 1. And there was a theorem by the first theorem, that is one of the first theorems in the area, is by Gage and Hamilton. And they said the following. If the initial curve, if gamma 0 is convex, then the evolution exists for a finite time. Well, convex, closed, embedded. For a finite time, and converges to a round point. So a round point means, so this statement here means that if I rescale the flow to have a fixed length, for instance, then it's going to convert to a circle. So I don't know if this color you can see anything. So what this means is that after rescaling, to keep, for instance, the length fixed, you can do other rescalings. To a circle. So this is the first theorem. And then a year later, of course, that doesn't fall in that category until this time. When it comes to this time, it's already in that theorem. But a year later, yeah. So it became convex and collapsed a point. There are a couple more actually in that web page. So you can play them at the same time. So after that, Grayson, with actually a lot of work, proved that for any gamma zero that is closed and embedded, then it becomes convex in finite time. In finite time. Okay, so this is sort of the complete picture in the case of curve shortening flow, or at least in the embedded case. And then there's a simpler proof of all the results together. By Husken. What he does is that he compares what is called the intrinsic distance. So to compares L with the extrinsic distance. So with D. So he compares L and D. This is very vague, but comparing L and D. And then the proof of Husken was simplified. Or at least made shorter, simplified by Andrews and Brian recently, maybe 5 years ago. So in the notes, this is the proof that I included, and if I have time today, maybe I'll talk a little bit about the proof, but for now I think I prefer to skip it to try to talk a little bit more about the other singularities. Okay, so in the case of curve shortening flow, we don't have any examples like the dumbbell example, and so bad things sort of start to happen in some sense in one dimension more, or maybe if you remove these conditions here. And there are some examples actually that I'm going to mention later on. Okay, so this is what I want to say about curve shortening flow. And then I'm going to talk a little bit about how we classify the singularities. This is one way of classifying. There are other classifications. I chose this because this is the more classical one, I would say. So before making the definition, let me go back to something that I sort of said yesterday, but not completely. That is the following. So singularities form. One can show using maximum principle that singularities form if and only if the second fundamental form goes to infinity. One can show that in the case that this is bounded, then everything is smooth. And yesterday we showed, in fact, we proved that a square is bigger than 1 over square root of 2t minus t. So I'm going to define this I'm going to make the following definition. If, well, let m of t be a solution, bless you, to mean curvature flow with singular time t, then if the limit of a squared times t minus t is bounded as t goes to t, we say the singularity is type 1. If not, it's type 2. Okay. So more or less the rest of the lecture, what I'm going to do is try to see what are the differences between these two things. Before I go with that, are there any questions of the previous thing? The previous stuff? No? It's all good? Okay, so basically, I'm going to treat in a different way the singularities type 1 and the type 2. In some sense, the type 2 are singularities that form faster than type 1. And the examples that we know how to compute, like the circle or the cylinder or the curves, they're all type 1. All the examples that I've shown you so far, they're all type 1. All the examples that we've seen are type 1. We've seen are type 1. So a reasonable question to ask is, are there any examples of type 2 singularities? Maybe all singularities are type 1. So are there any singularities type 2? Let me give you one of the few examples of type 2 singularities that I know. That is the following. Suppose that you start with something that is like this. This is not embedded anymore, so it's not really as in my theorem there. So this initial condition. So as you see, if this is smaller than that, so if intuition works here, I would say that all these are contracting, but this should be contracting faster than that one, right? So what you expect in finite time is that you will have something that is like this, in some sense. And in that case, one can compute that under certain conditions on the balancing these two sides, then actually this singularity is type 2. That's, I think, like the only examples that I know about type 2 singularities are all examples where embeddedness fail. So this is type 2. Sometimes. So a lot of the effort on the field is served to show that there are no singularities type 2. To first understand singularities type 1, and then to show that there are no singularities type 2. So I guess I'm going to spend more time on the type 1 for that reason. Okay. So the idea is that I have again the same setup as there. So let empty be evolution. And I want to know what can I say at this singular time about how the singularity looks like. A standard procedure to see how the singularity looks like is try to rescale the curve. For instance, in my example there, so I have something that has a very thin neck at some point maybe, and what I want to do is rescale, and make it bigger so I can understand how it looks like. Scale to see the singularity. And since I'm focusing here, what I'm going to see is probably a lot of the neck, and very, very far away, I'm going to see the rest of the surface. And when I take a limit, actually I'm not going to see anything but the area around that portion there. That's the idea of the rescaling I want to do. And I'm going to write exactly what kind of rescaling I want to do here. I want to get all the constants right. So consider the following rescale surface. So what I want to take is the following. Okay, so I'm going to take f tilde of omega t being minus some p. I'll say in a minute what this is. Of 2t minus t. Call that S. and S of t is minus 1/2 log t minus t. Okay, so this point here, this is morally where the singularity happens. So in my example before, basically 0 would be my p hat. That is the point that I know is singular, or something that is close to that. So this rescaled surface is not longer a solution to mean curvature flow, but satisfies an equation that is the following. Satisfy an equation that is the following. It satisfies that df ds tilde is equal to minus h tilde nu tilde. Let me see, as the way this is written, minus f plus f. Yeah, plus f. And S is something that is between 0, I guess. Let's see. When t is equal to 0 is minus log t. I don't care too much about the initial time, but the point is that it goes all the way to infinity. And also, if you look at the second fundamental form of this, it's equal to, so you have rescaling, right? So this rescales like 1 over the constant for the space time. So it's like this. T minus t. And this, I knew that it was bounded by something of this sort. So this is actually bounded. So this is something that exists for until infinite time and has a second fundamental form that is bounded. So the second derivatives are bounded. And using maximum principle like yesterday, you can actually show that not only this is bounded, but you can find local bounds for all the derivatives of this. So now you have a sequence of surfaces that have all the derivatives bounded. And what would you expect in that case? One would expect that then when S goes to infinity, this is converging to something. So we would expect that F tilde is converging to some F infinity. And if things are really very, very good, I also expect that the limit will have that this is 0, that the limit satisfies minus h nu infinity plus f infinity is 0, or what is equivalent is that f tilde infinity or h infinity it's nu infinity dot f. And if you were in the talk yesterday of the tank, he talked about surfaces of this type. He called these self-similar constructing solutions. So these are special kind of solutions, and they're very, I mean, they have been studied especially because of this, because they're models of singularities type 1. Okay? And of course, this is, I'm saying here that I expect things to converge, but I haven't proved that that happens. And we need something a bit more to prove that actually this happens. And the piece that is missing here to prove convergence, well, one thing is that one needs more than the derivatives being bounded, but also you need some local area bounds to prove convergence. And then there is sort of a standard procedure to prove that. And somehow I want to prove that this is going to 0, or that this equality is true in the element. And the ingredient that is missing here is what is called the Huske monotonicity formula. That is something that was, in some sense, mentioned yesterday tangentially. That says the following. It says that if you take a function that I'm going to define in a minute, t0, x, t, and t, mu t, and take the derivatives of that, this is exactly let me see. You get here h plus x dot nu, probably minus, because we're doing it this way, phi of x naught, t naught, the mu. And there's a minus sign missing here, where this function here is what they call the backwards hit kernel. That is, sorry, no integral here, e to the minus x naught squared 4 pi t minus t, or t naught minus t, in the way that is written there. T naught minus t. So if you have ever taken a PDE class, probably you have seen this, because this is the kernel for the heat equation, except that there's a sign that is changed. There's one, in the case of the heat kernel, you have that and that. So this is a backward heat kernel. This is a solution to this equation. Write a remark here. This is relevant when you're computing, but so that holds there, and that's why this equation holds partially. But I want to say what happens with this this equality when I rescale, and I have the following. It's even simpler in that case. The ddt of m tilde, so this is a rescale one, e to the minus y squared mu tilde t. H tilde t minus the statements that I'm missing to prove that can be deduced from this formula here. So what happens? For instance, if you integrate this on time, then you get that you are integrating this quantity, right? So it's this at some time and the time, first time and last time, let's say. And then you get a double integral of this quantity. So if this was not going to 0, that means that in some sense this weighted area is going to infinity. So the problem reduces to prove sort of area estimates on this thing. And this is something that can be done. I don't think I have time to do it if I want to go with all that plan. But the monotonicity formula implies that all those statements that I made there are true. In general, this not only for this flow, but in general for flows, having monotonicity formulas is usually very important to prove things like this, to study singularities and to prove convergence in long time or at the time of the singularity. There are other monotonicity formulas that I'm not going to present here, but I mean, there has been work on trying to find different monotonicity formulas. So, okay, so understanding singularities type 1 means trying to classify things that have this property. So, to understand singularities type 1, we need to classify surfaces that fulfill H is equal to X or to F dot new. I keep switching between F and X, but this is an F. Let's say. No, all these are F. So let me give you 2 points of view of this here. I'm not going to do much, and I'm just going to give you one result on that. But this is equivalent to say the following. That means that F or F tilde, let's say, that's a bad notation. Let me call this tilde, just to be consistent with what I had there. So if F is square root of T times F tilde, this is a solution to mean curvature flow that has always the same shape and contracts to a point at time T. This is what is called, this is a self-similar shrinking solution to mean curvature flow. And of these, we have talked at least about 2 examples. One are circles, and the other ones are cylinders, right? Those fulfill that. Spheres and cylinders. So actually, there's a result by Golding and Minicosi that says that if the surface is mean convex, we said yesterday that is something that is preserved by the flow, then generically, singularities are spheres and cylinder, and that's it. And the other important classification result in this line, and it has to do with the theorem that I mentioned before, is that for one-dimensional, for curves, all these are classified by a Brecht Langer, and the only embedded ones are circles. All the other ones are not embedded. Average and Langer. And the only embedded one is a circle. There are many, but they're not embedded. And they're nice pictures, but they're not embedded. So this is more or less what I have to say about type 1. And maybe I erased something that I shouldn't have erased. But if you see, for type 2, we cannot really do the same thing because when I rescale, I get something, I get the second fundamental form not being bounded. So it's not exactly, I cannot prove any convergence if I don't have the derivatives bounded. So this is all true if it's type 1, but if it's type 2, I need to do something else. And there's an idea by Hamilton that is something that he used for the Ricci flow on how to try to do a similar procedure but different rescaling for singularities type 2. We need to do a different rescaling. The rescaling that I'm going to propose now, you can actually do it for, you can also do it for type 1, but what you get is not maybe that interesting. You're rescaling too much in some sense. So, okay, so first we need to choose a sequence of pk and tk such that a of pk tk squared of t. So this is close to a singular time in principle. K and P in M. I keep finding typos when I read this. So basically, what I'm doing here, just to be clear on what this means, I want to approach the singular time and the singular point in a special way to be able to rescale. And when you do the estimates, you can see why this is the correct rescaling, or a correct rescaling, I guess. And define Fk of omega s pk tk tk plus tk minus pk And by doing this, let me see where this is defined. That is important here. APK TK square TK squared, and then exactly that. T minus 1 over K minus TK. Okay, so this is the rescaling that I want to do. So, for one thing, because of the way that I redefine, I mean nothing here, these are constants for time, this is still a solution to mean curvature flow. And by multiplying by this, I'm sort of forcing the second fundamental form to be bounded for this sequence. So there are solutions to mean curvature flow with bounded second fundamental form for not all the time, but almost all the time by the way I chose. So almost until the end. So one can show, it's not very hard to show that because of the choice I made and because everything is bounded, then I will have that these actually do converge and this interval becomes an infinite interval in both directions. One can show, I'm not going to go into details, but one can show that fk converges to f infinity, and f infinity is a solution to mean curvature flow in minus infinity infinity. So it's a solution that is defined for all time, so it's something quite special. This type of solution is called an eternal solution. So it's an eternal solution to mean curvature flow. In the first day, I show you an example of an eternal solution that was this translating soliton, the Grim Reaper, and that's the only one for curves, actually. The Grim Reaper is the only embedded eternal solution for curves. One more remark here, because of the comparison that we saw yesterday, these are all things that are non-compact. They cannot be compact. So let me make those two remarks. These solutions have to be non-compact. And for curves, the Grim Reaper is the only eternal solution. So as understanding singularities type 1 is the same as understanding self-similar shrinking solutions, understanding type 2 means to understand things that are eternal. And, okay, so maybe I will talk about this more tomorrow. I don't know. It's time, right? Yeah, so I'm going to finish here. My plan for tomorrow was to talk about things that are not compact, but maybe I will start with the last part that I'm missing today, that is how to continue the flow.
Any question or comment? ¿Alguna pregunta? ¿Comentarios?